Hi, good morning everybody. We are back with rate processes. So in our last lecture we talked about the ultrafast processes in chemistry. Now these ultrafast processes are very important and in many respects. So some of the probing of this ultrafast processes is very important in respect of the fact that it gives us new insight on the understanding of chemical reaction, especially probing transition state of reaction. So and on that ground we discussed many techniques, of which one is pump probe technique, which is the modified version of the faster version of this laser flash photolysis. Okay, and we also tried to give outline of how this transition state can be probed using ultra short laser pulses. So today we will still continue with this, and under the heading of time resolved emission spectroscopy, talked about that it is a technique which is called the time correlated single photon counting technique, which is based on counting of photons. Okay, and immediately after the excitation pulse enters into the fluorescent sample, that starts some process. Okay, that may be photophysical process, maybe some photochemical process. Photophysical process may be, like I discussed, this solvation dynamics of solvation, how these solvents are oriented around this transient dipole that is created as a result of excitation by photons of appropriate frequency. So the time correlated, this technique TCSPC or time correlated single photon counting technique, that is that has this span around in between 1 picosecond to several nanoseconds, and even above 1 nanosecond as well, like say tens of nanoseconds we can do that. Okay, and this single shot measurement, that is another way of looking into the ultra fast or maybe faster processes. Of course, that does not go into ultra fast region. Single shot measurement, that is you shine with a single shot of laser pulse, single shot of laser, and then you measure the emergent light. Okay, that is emergent probe light, or maybe measure if any spontaneously emitting light is coming out of your solution. In case of time correlated single photon counting methodology, there you excite your sample with a brief pulse of radiation, and this spontaneous emission is coming out of the solution, or that emission may be coming out of the solution due to some chemical reaction as well. Okay, and there is another technique which is called the up conversion technique that I also talked about, which is basically some frequency generation technique, that you generate you amalgamate two frequencies in a specific through a specific media that is showing nonlinear optical properties. So exploiting the nonlinear optical properties of certain materials, we can join two photons, okay, to generate one photon, and by some specific, using some specific protocol, we can find out the time dependence of your sample decay. Okay, how the sample is decaying as a function of time. So these are the ways that you can do time resolved emission spectroscopy. Single shot photoluminescent measurement, which is the temporal resolution, is limited by the detector, which is of the order of say 20 nanosecond, and can collect the data in one shot of laser, okay, in macroscopic systems. Okay. Now here you have got the photoluminescence decay measurement, that what is happening, that you shine, you get it is here you use a pulsed laser, that is ND-YAG laser, or maybe titanium sapphire laser. Okay. So then you collimate it, then with the help of a beam splitter you have a fast photodiode which triggers your digital oscilloscope. Okay. And maybe a very little percentage of your this laser light, maybe it is a blue, say it is a blue light, blue lasing light, so maybe 1% or even less than that, okay, is directed to your fast photodiode. That is, it is responding very fast. The moment light is falling on the photodiode, it gives a trigger pulse which triggers your oscilloscope, digital oscilloscope, and the remaining 99% of your laser light, which is falling on the sample, okay, which is falling on the sample, and then it is, the emission is collected at 90 degree, because if you collect emission, and this is called your dump, that the excess of lasing light which is coming out of the solution in this side is absorbed by some material, some medium, so that the excess light is not going somewhere else, because that may create some hazards. That is why it is dumped, and this luminescence is collected by an optics appropriate type. So so that is appropriate optics has been used up. So then it is collected by a spectrometer. Okay. So spectrometer, and then the outgoing light from the spectrometer is collected by a photo multiplier tube, which is a maybe generally the detector is temporal resolution could be of the order of nanoseconds. Okay. So this photomultiplier signal is fed into digital oscilloscope. Now the oscilloscope collects the signal, but the point is that the moment this fast photodiode receives a signal from the beam splitter, then photodiode puts a trigger onto the oscilloscope, so that the oscilloscope is ready. So after this trigger is on, maybe this oscilloscope remains on for maybe several microseconds. So between the trigger and maybe say after up to 100 microseconds, this oscilloscope is ready to receive any signal, and if any signal is coming out of the PMT, then this digital oscilloscope digitizes that signal and it shows on its display. So it is a typical decay profile. So typical luminescence decay profile. Okay. So this temporal resolution is limited by the detector, and it can collect data in one shot of the laser. But the thing is that, and the digital oscilloscope, the whatever signal it is collecting over here, can be fed into a PC for further processing of the data. Okay. Suppose in the one shot, if your signal is not very smooth, okay, if it is noisy, then you may average that signal for maybe this decay maybe for 100 shots, maybe 50 shots, maybe 25 shots, depending on how good is the signal quality. If the signal quality is very high, then maybe in one shot it is okay. Okay, so this is the way you can also collect a fast decaying profile. Okay, so fluorescence profile you can collect. Okay, and this fluorescence may be, this profile may be correlated with some photophysical phenomena or maybe some photochemical phenomena, because that fluorescence may be this green fluorescence, say whatever you are getting or whatever is coming out of the sample may be due to a photophysical process or maybe due to some chemical process as well. Suppose because of some chemical reaction photon is liberated. So that photon, how this photon is changing its intensity as a function of time, that we can measure. And the use of the spectrometer, the usefulness of the spectrometer is that you can resolve these emission, okay, into a number of frequencies, because it may not be a single frequency that it is giving sometime, and in most of the cases the fluorescent materials they have a broad emission band. So you can collect emission as a function of different wavelengths. So maybe at one wavelength the decay profile is different than the other wavelength. So from that some complicated reactions or a complicated scheme can be probed into. Okay, so that's a typical diagram for single shot photoluminescence decay measurement. Next, time resolved luminescence, that I told you that time correlated single photon counting, that is the basic apparatus that you have got your maybe about 100 femtosecond pulse, maybe 360 to 470 nanometer 100 femtosecond pulse, again with the help of a beam splitter. A fast photodiode is this maybe 1% of this laser light is directed to the fast photodiode, and the remaining 99% is fed into the sample, and then here the same it is collected. Okay, and in this case the thing is that your detector is a different kind of detector. It is not a simple slow detector as I talked about here, photomultiplier tube. It's a special kind of detector called MCP-PMT. Okay, so microchannel plate photomultiplier tube. It has got a good time resolution. Okay, so in that case, that is detection, time resolution is not that much limited like the earlier case. So it can give you good time resolution. And here the spectrometer again is used over here for resolving your emission as a function of different emission intensity, as a function of different wavelengths, and you can measure the decay profile in terms of a histogram as a function of time. Okay, that is number of photons that is collected at different times. Okay, different time gap. So here what happens, that the moment laser falls on the beam splitter, it triggers a photodiode, and then a signal is fed into this it is called the correlator, and fed into this box, and so this is ready to receive ready to receive the another photon from the MCP-PMT. The moment MCP-PMT receives another photon, then it stops. So number of photons that is received in between this is now converted, and then it is fed into a personal computer, and a histogram is generated. So this is basically a decay profile. Okay, so this way you can do the time correlated single photon counting measurements. Okay, so this is another fast techniques. So by this you can probe many things like solvation dynamics. If this dynamics of solvation is not like 1 or 2 femtosecond or maybe 100 femtosecond, then you can easily do that. maybe if its time resolution is about say 40 picosecond, say 20 picosecond, then you can do quite a fast processes. Okay. So, this way you can do time resolved luminescence experiment like a single shot. It is not a single shot one, but it is a different way that you find out the correlated photons. You collect the measure the number of correlated photons that you are getting, which is called the time correlated single photon counting. Okay. So, TCSPC is temporal resolution is of the order of 50 picosecond. Okay. And it is not that much limited. I like single shot photoluminescence where 20 nanosecond resolution, but here its temporal resolution is 50 picosecond, and its excitation range can be 470 to 360, emission range can be 300 to 900, and nowadays different sources are available by which even you can excite a little at little longer frequencies, I mean wavelengths, and works excellent on time scale which is less than 50 nanosecond, and on longer time scales data collection time may be quite long. Sometime it may be quite long, because you have to collect the data for a long time, because you have to shine your sample for quite a long time, and you have to collect those single photons that is coming out of your sample by the help of this this fast detector. Okay. So, collection time may be very long, depending on whether it's a weakly fluorescent material or it's a strongly fluorescent material. Okay. And it's a very sensitive apparatus. Okay. And works well with low emission yield materials. Okay. And resolution is limited by the jitter and width of the detector response. So, there are other factors which may complicate the issue of the time resolution. Okay. So, that we are not going to discuss over here, but maybe some other factors are important, like as I told you, like jitter and the width of detector response. Okay. So, this TCSPC is another very nice technique by which you can probe this very fast processes like solvation dynamics, maybe excited state intramolecular proton transfer reaction. Like suppose you have got a species, say like something like this, say hydroxybenzaldehyde. Okay, like this. Okay. So, this makes a hydrogen bond over here. Okay. Ground state there is a hydrogen bond, but in the excited state what happens that this this proton is transferred from here to here, which is called the excited state, and it is through intramolecular hydrogen bond. So, excited state intramolecular proton transfer. So, you can probe this process. This is a very fast process. Okay. So, you excite, then you generate your excited state species, which is denoted by star, and then in excited state the acid base properties differ considerably than in the ground state. So, it snatches this proton, and thereby maybe this species is generated that this way and this. So, you can probe this process, because your this is a tautomer and this is your normal. So, tautomer and normal can have different absorption wavelengths or maybe fluorescence wavelengths. So, you can monitor maybe at this monitor for this species or maybe for this species, and with as a function of time you can monitor how the intensity of your fluorescence or maybe absorption intensity is changing as a function of time. So, if you want to monitor by fluorescence method, then maybe TCSPC will be one of the best options to look into this excited state intramolecular proton transfer process. So, that is a fast process. So, that is one very important use of this this technique. So, fast processes like this atom transfer or proton transfer, that can be proved by this ultrafast technique. So, we can follow the rate of this transfer of this proton from one atom to another, and what are the factors by which this proton transfer can be, or maybe this atom transfer can be modulated, that you can also follow, okay, by changing maybe the solvent, or maybe introducing something else, maybe putting this system into some say maybe in micellar environment, or maybe in a cyclodextrin cavity, or maybe somewhere else. So, that how the environment can affect this proton transfer process, that we can follow, whether it becomes still faster or maybe it becomes slower. Okay. So, we can look into that. Luminescence upconversion, as I told you, I have given you brief idea that again here in this case say you are using say 100 frame per second 800 nanometer red light, okay, from your titanium sapphire laser, and then it is divided into two parts. One is directed this way, okay, and which will be used as the gate pulse, okay, and the other portion is fed into a second harmonic crystal. Second harmonic crystal basically generates the second harmonic, that is 2 photons of same frequency. These two are amalgamated, and that is also a non-linear process. So, you have to focus this 800 nanometer beam tightly onto this SHG crystal, so that the output will be a blue one, okay. Then you have with the help of a lens, you can let this light to fall on the sample more tightly, so that the luminescence is coming out of this sample. So, it is a luminescent sample, and this luminescent sample, luminescence is again collected with the help of a lens, and then it is focused onto another upconversion crystal, that is again a non-linear crystal, and that has to be put onto this crystal at a specific angle. Not all angle will do your business, your job. So, then this is focused onto here, and this gate pulse is then allowed to fall on this focused point, so that these two frequencies will make a mix, and thereby generating a mixed frequency, upconverted frequency. Okay. So, this side, these two are the dumps, that is excess light will be dumped, and maybe at a specific angle this is collected. At a specific angle, your this upconverted light is collected by a spectrometer, and then it is the detector, and then this detector signal is fed into a digitizing system, maybe a PC. Okay. So, here this your luminescence contains a number of frequencies. Okay. So, what will happen that because it is not a single wavelength, because emission is a different it's a combination of frequencies. Okay. So, you will be getting a number of frequencies over here, and then this is as it is fed into the spectrometer, then you collect your signal. Now, the thing is that how to generate your time axis, because this spectrometer, what it does is basically this collecting the signal or the time integrated signal, because you remain maybe at a given time point and allow the spectrometer to collect the signal and integrate for a long time, so that your noise is minimized, and then that signal number or signal intensity information is fed into the computer, so that you generate a point, that is a signal point corresponding to a signal. But how to generate your x axis? In that case, in the same way as we talked about for palm probe, that you use a retro reflector, pair of mirrors, and so here the optical path traveled by red and the optical path traveled through this. Okay. When these two exactly match or exactly equals, then it is your time 0, and then you progressively delay or advance this gate pulse to generate your time axis, so that ultimately you generate your this decay profile like this. So it is your delay. Delay corresponds to the delay between your gate and your fluorescence. Okay, and this is your fluorescence intensity. So you collect it and then you fit with some mathematical formula, so that you can find out the kinetics of the decay. I mean decay kinetics, that is the time required for the intensity to drop down to some value, or maybe it can give rise to some rising signal as well, depending on the system of interest. Okay. Palm probe, as I told you, and that palm probe is another way of looking into nonlinear processes, as I already have talked about. Okay. And pump, like basically you pump over here, and then maybe you can probe from here to here. There is an absorption process, or maybe it is an emission process. Okay. So so there are various complications maybe there, which we are not going to discuss in detail. So basically palm probe experiment, in palm probe experiment, one enables one to trace the relaxation dynamics with sub 100 frame per second resolution. So it has got a quite good good resolution. Types of data generated by palm probe experiment: time resolved absorption spectra and absorption transients at is time resolved absorption spectra and absorption transients at a certain wavelength. So these are the types of data that is generated by palm probe experiment. Numerous combinations of pump and probe beams are possible. Okay. UV pump, visible probe. As I told you, it may be one color, it may be two color. Okay. Or one case UV pump, visible probe, in another case UV pump, continuum probe, maybe blue pump, blue probe. Okay. The beauty of this method is that since you are using the short pulse, therefore its frequency resolution is not that much. So it is a it is more dispersed. So bandwidth is more. Okay, because it is time wise it is short, but its bandwidth is more. So it enables one to measure at different wavelengths as well. High pump intensities are required in order to produce noticeable change in optical absorption of sample. Okay, gigawatt or terawatt. Okay, now Timeresolved amplifiers are generally used. Okay, and sometimes your interpretation of data is complicated. Okay, because of the processes that are going on in the sample after your photo excitation or after pumping the sample, could lead to complicated photophysics, or maybe could lead to complicated photochemistry. Okay. You can use these ultrafast techniques to probe into semiconductor quantum dots. These semiconductor quantum dots are between bulk material and atoms. So interesting photochemistry, I mean interesting photophysics, or maybe photochemistry can be looked into by this ultrafast processes. Okay, so that's another possibility. This is a typical transient absorption spectroscopy for cadmium selenium quantum dot, taken from this reference. So where we see in one case, just I am giving you the typical idea that this transient absorption spectroscopy can also be used for this quantum dots, because quantum dots are nowadays a very hot topic. Okay, so this nanotechnology, advancement of nanotechnology and nanomaterial research is a very interesting field nowadays. So So, using this transient absorption spectroscopy, we can look into various photophysical or maybe photochemical aspects of this materials. So, it has got a tremendous application. Okay. So, here again these guys have reported some time dependent behavior, okay, which right now we are not going to discuss in detail, but that can be useful. Next, we will look into this femtosecond light activated processes in biology, okay, or maybe biochemical systems. Okay. So, these proteins, okay, in this case chromophores, okay, chromophores could be proteins, okay, because these proteins have these proteins have many chromophoric groups, and maybe light sensitive substances, light sensitive molecules can be chromophores as well, because proteins contain amino acid residues. It may be your this aliphatic amino acid, maybe aromatic amino acids. Okay, it may contain chromophoric groups like that group which is available with tryptophan, maybe tyrosine. So, chromophores are available over there. So, protein itself can act as chromophore, that if you shine with radiation of appropriate frequency, it will emit. Like if you excite a protein sample containing tryptophan residue with 295 nanometer of light. So, that 295 nanometer of light selectively excites this tryptophan residue, and thereby emission is generated. Emission is coming out of the sample, okay, and maybe probing that emission and probing the emission characteristics of that protein, we can look into various various aspects of proteins like binding or maybe reaction, so that we can probe whether this protein is this unfolding or whether it is refolding, because if a protein is unfolding and if your tryptophan residue is coming from inner maybe hydrophobic core to the outside solvent exposed situation like water, then its emission is tremendously reduced. Okay. So, therefore, by looking into the emission intensity of your tryptophan residue as a function of time, okay, we can probe this your folding dynamics, folding kinetics, we can probe into. So, therefore this is very important, that using time dependent behavior of protein fluorescence, and sometimes it happens in femtosecond time scale as well, not only in slower time scale, but also in femtosecond time scale. So, in femtosecond time scale, lot of interesting things may happen, and that can give us important information about what is going on immediately after photoexcitation, maybe some breakage of bond, maybe some restructuring, maybe rearrangement within the molecule, within a molecular system, and that we can follow with ultrafast spectroscopy. Okay. Now, photosensory proteins, okay, like which are responsible in vision, that is we can look, we can see. So, there is a mechanism, photochemical mechanism, photochemical reaction going on the moment light falls on our eyes. Okay. So, photosensory proteins are important, and then phototaxis, plant growth. So, these are very important. So, these are light driven processes, light driven rate processes. Okay. So, like light falls on something, on some molecule, then it does some chemical reaction, and the end product of chemical reaction may lead to something new. maybe that lead to some output like vision, maybe phototaxis, maybe plant growth. Okay. So, it is a typical structure of this photosensory proteins. I mean a domain, I mean a part which is photosensitive, which has got photosensory property. So, understanding of the molecular physics behind this these phenomena like vision, phototaxis, plant growth is of immense importance. So, what is the molecule? I mean we wanted to know the physics at the molecular level, and also the rate processes involved over there. What are the exact rate processes that are going on? What could be the mechanism of such an ultrafast process? Okay. So, this is very important. Like as I told you, this dissociation of hemoglobin. Okay. So, like dissociation of I mean hemoglobin oxygen bound, or maybe when oxygen leaves. So, ligated hemoglobin then when gives this oxygen to your cells, then dissociation of this hemoglobin oxygen bond, I mean iron oxygen bond is dissociated. Okay. So, how this is occurring? Okay, I mean in time scale, what is happening? Okay. So, this can be probed into by the use of this ultrafast spectroscopy. Like I gave you one example last in the last lecture, that carbon monoxide binds with hemoglobin, giving rise to carboxy hemoglobin. Okay. And that particular material is very stable. Okay. Now the moment you shine with radiation of appropriate frequency, then this this iron carbon monoxide bond is broken. Okay. And this carbon monoxide will tend to go outside the protein matrix. So, whether it is really going outside the protein matrix or not, that you can probe. So, using ultrafast processes, I mean ultrafast spectroscopy, you can you can do this the way it means you can look into the exact processes or the inner mechanism. Okay. Light is falling, then it is detached, and then it is going outside. Okay. Outside your protein matrix, or maybe outside your central metal. Okay. This is the metal. Okay. Initially this was maybe carbon monoxide, the light falls and then it dissociates. So, what is the dynamics? I mean how this is coming out? Okay. Is there any specific channel by which it is going out, or maybe it remains over there for a long time? Okay. So, photophysics of that, I mean probing of the photophysics of that process could be very interesting and can give us enough information about what is exactly going on, and also doing some mutational studies over here. Maybe you mutate some of the residues along the channel through which it is migrating from one region to another. Okay. If you mutate maybe few amino acid residues along the path of this outgoing ligand, if you mutate, then maybe you change the the barrier for for barrier that this molecule is facing while it is coming out, or maybe it is trying to rebind with this iron. So, that may be affected. So, by this by doing this biochemical modification, maybe mutational modification of this protein pocket, you can gain enough insight onto this rate process which is going on inside this cavity, inside this hemoglobin, when carbon monoxide is bound, or when you shine with radiation it is detaching. Okay. So, that is one very important topic, but we are not going into much details of that, but just we wanted to I wanted to give you the idea, the use of idea of how this ultrafast spectroscopy and probing of red phenomena can lead to enough understanding of the of the nature of bond or nature of bonding that is there, and further like as I told you over here about the path it is taking after the reaction is proceeding, whether this is going this way or maybe the other way around. Next is another thing is photochemistry of vision. Okay. So, it is basically retinal. So, 11 cis to all trans retinal. Okay. So, what is happening that if you shine with radiation of say h nu, then see a rotation about this bond. Okay. A rotation about this bond, that is 11, you see 11 C's, 11 C's, okay, and here all trans. So, you shine with radiation, then maybe a partial single bond character comes in, and then rotation about this bond occurs, leading to this structure. So, that is the key ingredient for our vision. Okay. So, this retinal 11 cis to all trans retinal, and this if you look into the absorption spectrum, then one will absorb at a different wavelength than the other one. Okay. And in certain period of time one is growing. Okay. After say 200 frames per second, one is growing from the other. So, what is happening that if you probe into this particular region, say 495, then with time we will be seeing that it is decaying, I mean it is reducing, and this is growing. Okay. So, by looking into this decay kinetics or maybe rise kinetics or growth kinetics, we can follow the exact time dependence of the process. Okay. And that is possible if you use ultra short laser pulses, maybe 10-15 frames per second pulses. Okay. So, in that case you can probe this processes as fast as several hundreds of frames per second, maybe 50 frames per second to maybe 200 frames per second or like that. Okay. So, so employing this frames per second spectroscopy, we can again, as I told you, in connection with your this carbon monoxide dissociation in hemoglobin, that it has been found that after dissociation it tends to rebind. Okay, it has got a rebinding kinetics and this rebinding can be altered by mutation. So, it has got two options, it will rebind and maybe it will leave the cavity, I mean leave the pocket, this heme pocket. Okay. So, so the point is probing into these things will give us enough insight onto the process. Okay. That here you see that when you shine with h nu, then this bond double bond character is lost, so that rotation about this single bond, I mean this would be single bond will lead to this all trans. Okay. What is the actual scheme? Scheme is like this, that 11 cis retinal, okay, then through this schemes, okay, I mean through this various steps, it is again converted to retinol and then retinol to retinal. Okay. So, what is happening that 11 cis retinal, then rhodopsin, then it is going to all trans retinal, then involvement of NADPH to NADP plus, it is giving rise to all trans retinol, then all trans retinal ester, then 11 cis retinol. Okay. So, it is the visual cycle, and this is taken from this reference. Okay. So, it is a complicated event, it is a complicated event involving many things. Okay. So, you can in principle means using femtosecond spectroscopy you can see this red process, because ordinary conventional kinetic measurements you cannot see, because it is several femtosecond process. Remember, femtosecond is minus 15, 10 to the power minus 15. So, how can you do it in a laboratory using a pipette or burette or maybe some titration? It is not possible, because it happens the moment it is falling. To us it is like that, the moment it is falling it is happening, moment it is the photon is hitting it is happening. So, it is very fast, it does not take give any time. So, how can you see it, how can you look into this very fast process? So, that is why the importance of this ultrafast spectroscopy, ultrafast spectroscopic technique is that you can see, because of the advent of this ultra short laser pulses, you can see this, you can visualize, and you can monitor it, you can in principle see it experimentally, that it is converting from here to here, that one substance is growing, another substance is decaying. So, substance is growth and decay, these are complemented, it is a complementary event. Okay, that is why it is very important this ultrafast application of this ultrafast laser spectroscopy is very important, especially probing into this ultrafast processes, which using conventional techniques like stuff flow, maybe plug flow, maybe relaxation mechanism, or maybe pump probe like flash photolithography, you cannot see. That is why it is a very important thing, that is this ultrafast spectroscopy is important in probing into this this ultrafast red processes. Okay. And the protein environment controls at which bond the chromophore will turn, means whether like here this turn and here this rotation will take place, or in some other point, or at some other point. Okay. Now, because of this when you shine with radiation, the electron cloud, because it goes into the excited state, goes to the excited state. So, electron cloud, I mean electron distribution is different from that of the ground state. So, electron cloud is getting distorted, okay, as the chromophore is excited with light. Okay. So, results in photo-induced charge transfer. Okay. When you shine with radiation, there is another possibility is that electron cloud, when gets modified, it results in photo-induced charge transfer, okay, and change in dipole moment, as it happens in case of solvation dynamics. Okay. So, in case of this visual cycle, that which bond will turn, means which bond will rotate, that is dictated by the dictated by your protein environment. At the same time, you have to remember that when if because of your photo excitation, electron cloud gets distorted, so maybe there is a possibility of charge transfer as well. So, when there is a possibility of charge transfer, means generation of a dipole moment, generation of a dipole, or maybe change of a dipole. So, when there is a change of dipole, then what do you expect? That dipole will tend to get solvated. Okay. So, there is a schematic that, as it is already shown to you, that your dipole is here, okay, because of photo excitation. So, dipole solvation is possible, that immediately after photo excitation, what happens is that these dipoles are at the ground state. I know this is your ground state configuration of the solvent dipoles, and the moment it is excited, the solvent molecules still remain in the Frank-Condon configuration. Okay. So, for Frank-Condon configuration means that it is still to get relaxed. Okay. The moment it is generated, it will start to rotate to give you the stabilized geometry. So, it will take time, and after some time the system will be solvated in such a way that it has got some lower energy. Okay. So this way, you can also follow solvation dynamics in protein environment. So how this, this water is maybe bound to protein molecule, or maybe biomolecular bound protein, I mean bound water or bound solvent. So how these solvents will respond to newly formed dipole because of photoexcitation. So you can follow the dielectric response of the protein environment, so that you can get information on the pockets of the protein concerned. So that's why this ultrafast spectroscopy in that respect is important. So it is time dependent Stokes shift. Okay, so what we have learned over here, that in ultrafast, we have given you the idea of this various techniques in faster and ultrafast time scale. Okay, and then its application, probably application maybe in semiconductor. We just have not elaborated it, but it can be used in materials research as well. Okay. Then femtosecond, in terms of femtosecond, application of femtosecond spectroscopy in light activated processes, that these light activated processes are very important in biology, especially which another important aspect is that light activated, maybe you may have some chemical substances which are at room normal situation they are not doing anything, but if you excite with light, it shows some antiviral activity. And again, those antiviral substances, light activated antiviral substances like hypericin, hypocrelin, or many other substances. So they will tend to kill viruses, showing some antiviral activity. So how this antiviral action is happening, or what is exactly happening immediately after photoexcitation to these molecules, what rate processes are involved, that you can probe. In the same way, we also have given you the idea that this visual cycle, what is happening in the visual cycle, or means how you can probe into the cavity of some protein like hemoglobin carbon monoxide complex. So what happens when you shine with carbon monoxide, whether it detaches, if it detaches, what happens. So these are the aspects that we have we have tried to give you the idea, but not exactly in detail because of the limitation of the scope. So that may be you can if you want to know more on this, you can consult any standard text or maybe textbook on femtochemistry application, maybe application in femtosecond spectroscopy in biology, femtobiology, femtochemistry, femtobiology, or maybe application of ultrafast spectroscopy in materials research, that you can consult. There are plenty of textbooks available in literature. Maybe internet resources are also available. Okay, so I guess that's all for ultrafast processes as far as introductory things are concerned. So we are not going to detail into these things. So in the next piece of lecture, we are going to take up molecular reaction dynamics. Okay, so molecular reaction dynamics, so we know is it is basically in this case again we will recap some of our old parts of this lecture series. Okay, and we'll try to have a link with the modern version, I mean understanding of reaction dynamics with chemical kinetics, what we have learned so far. I mean how this concepts of molecular reaction dynamics can be translated into the reactions, or maybe into the aspects that we tried to learn so far. Okay, so that will be taken up, that is concepts and applications, those things will be taken up in the next lecture with the heading reaction dynamics. Till then, thank you.